So this lesson is an introduction to limits. And before I get into it, I just want to tell you that what happens at the point isn't our concern. It's what happens near that value. So that's what I need you to focus on. Focus on the behavior of the function near the value of interest. Near is the key word. So the first example I'm going to look at is the following. I'm going to let f of x equal x squared plus 3x minus 2. And I am interested in the limit as x approaches 1 of f of x. So if I choose values that are fairly close to 1, x values that are fairly close to 1, what are the f of x values getting very close to? That's what we're trying to answer. That's our basic idea here. So to do that, I'm going to go ahead and use the graphing calculator and choose x values fairly close to 1. So I'm going to pull the graphing calculator up. And I plug in the value of the function with the y equals button. And I have x squared plus 3x minus 2. X squared plus 3x minus 2. And we are interested in what happens near 1. What happens at 1 is irrelevant. What happens near 1 is what we're interested in. So we can go to vars, y vars, function. What happens near 1? Well, I don't know, is 0.8 near 1? So that's my x value. The corresponding value of the function is 1.04. Okay, let's get closer to 1. If I do second enter, that brings up the previous line of code and I can edit it. How about 0.9? So that's getting closer to 1, and the value is 1.51. But I can get even closer to 1. And I try to identify some sort of a pattern to see what's happening. Where do we think the values of the function are getting closer and closer to? What are the y values getting closer and closer to? Now you may say, boy, 1.95, 1.995, they certainly seem to be stabilizing closer to some number. And you can hypothesize what you think that's going to be. Probably going to be 2. And we'll do one more just to see if the pattern holds. Just add a few more 9s and maybe a 7 at the end, just to be a little different. Do we get a number fairly close to 2? We sure do. So by choosing numbers close to 1, we seem to be getting values of the function that are close to 2, which indicates to us that maybe that limit is 2. But we've only chosen numbers less than 1. Notice 0.9, 0.99, 0.999, 0.9999997. That's not enough. You've actually got to choose numbers on both sides. So I could also choose 1.1. Oops, I'll just go ahead and type it in again. Vars, y vars, function of 1.1. That's pretty close to 1. Do I get a number fairly close to 2? Maybe. Vars, y vars, function y1, how about 1.001? What do I get? A number pretty close to 2. And let's see if that pattern continues with a number even closer to 1. Now this, again, this is not a proof. That's a number pretty close to 1. Is the result, is the value of the function pretty close to 2? It sure seems to be. So what do we conclude about that? What do we say? Well, this was our question. As we approached from the left, as we examined x values to the left of 1, the values of the function seemed to be getting closer and closer to 2. So what is the notation that we say for that? Again, the numbers to the left of 1 were things like 0.9, 0.99, 0.99997, whatever. Numbers to the left of 1, but getting closer and closer to 1. And the values of the function we had, 1.995, 1.999985, they seem to be getting closer and closer to 2. The way we write that is, we say the limit as x approaches 1 from the left. This is the notation that we use. This is, again, not a proof, but it seems to be it seemed to be 2. Similarly, as we approached 1 from the right, so as we examined x values to the right of 1, the values of the function also seem to be getting closer and closer to 2. So the notation we use for that, no surprise, is similar to this, except as we approach it from the right, we change that to a plus sign. So we have shown, at least we are hypothesizing, approaching from the left, the values of the function get closer and closer to 2. Approaching from the right, the values of the functions seem to be getting closer and closer to 2. And in that case, when the limit from the left is the same as the limit from the right, then we say that the limit exists. So when the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x, we say the limit as x approaches c of f of x exists, and its value is that shared value, right? And the limit as x approaches c of f of x is the same as the limit as x approaches c to the left of f of x, which is the same as the limit as x approaches c to the right of f of x. So in our example, what did we show? We showed the limit as you approached 1 from the left equaled 2. So the limit as x approaches 1 from the right also equals 2. So our conclusion here in our example, the limit as x approached 1 of f of x, which was equal to the limit as x approaches 1 of x squared plus 3x minus 2, was the same as what? Was the same as 2, because the limit from the left and the limit from the right were the same. Now, you may have noticed something. We are interested in the limit as x approaches 1 of f of x, which is the same as the limit as x approaches 1 of x squared plus 3x minus 2. Now, what we said on the very first page is focus on the behavior of the function near the value of interest. So focus on numbers near 1. Do not focus on what happens at 1. Well, if you notice something here, what if I plug 1 into the function? If I plug 1 into the function, what is f evaluated at 1? 1 squared plus 3 times 1 minus 2. 1 plus 4 minus 2 equals 2. Is that a coincidence? Is that always going to be the same? No. No. When they are the same, when the value of the function is the same as the limit, that is going to define something called continuity. The graph will be unbroken in a sense at that point. But we cannot assume that all you need to do is plug in the number to get the value of the limit. So let me show you an example that gets at that. Let g of x equal x squared minus x minus 6 over x minus 3. And I am interested in the limit as x approaches 3 of g of x. Now, before we do this, remember what happens near 3 is what we're interested in. What's happening near 3? Well, at 3, g of 3 would make the bottom 3 minus 3, put a 0 downstairs. So g of 3 does not exist. So I can't just plug in the value and see what I get for that. There is no value for g of 3. So what I need to do instead is I need to look at values near 3. So following the same pattern I did in the last problem, numbers near 3 to the left and to the right. To the left, I'll choose 2.9, 2.99, and 2.999. And let's see how those behave. So again, I'm going to go ahead and look at the graphing calculator. And I'm going to change my function. So I'm going to clear that one out. I'm going to put the new one in, parentheses x squared minus x minus 6. Divided by parentheses x minus 3. And I told you that that's our g of x, but also y1 according to the graphing calculator. So if I try to plug in 3, I would have a division by 0. And notice that's what it tells me. It's an error. So let's try something else. Let's try numbers near 3. Let's go with 2.9. If I plug in 2.9 into the function, what do we get? We get 4.9. If I go to 2.99, gives me 4.99, and we're starting to see a pattern here. If I go to 2.999, let's just take a look at one more to convince ourselves that the pattern continues. Second, enter. If I go to 2.999, indeed 4.999. So what does that tell me? What does that tell me? As I am approaching 3 from the left, those numbers, the values of the function, we approach x. The x values approach 3 from the left. What do the f of x values do? G of x values seem to approach 5. So it appears to me as if the limit as x approaches 3 from the left of g of x looks to me like it's going to be equal to 5. But how about approaching it from the right? So I would need 3.1, 3.01, 3.001, or something similar. Numbers getting closer and closer to 3. So let's go back to the graphing calculator. This time I'm going to use the table function just to ease that a little bit. So second table set, we're going to go to ask, and then second table. Just to show you how this works, I used 2.9 before, and 2.99, 2.999. And now we're going to choose numbers close to 3. So how about 3.1? Gives us 5.1. 3.01 gives us 5.01. And 3.001 gives us 5.001. So what does it appear that those numbers are getting closer and closer to? Well, as the x values get closer to 3 from the right side, 5.1, 5.01, 5.001 sure seem to be getting closer and closer to 5. So what we could say there is we could say the limit as x approaches 3 from the right of g of x is also 5. So what is our conclusion? What is our conclusion? The limit from the left is the same as the limit from the right. That means the limit exists, even though the function doesn't. G of 3 did not exist. If I plugged in 3, it gave me a division by 0 thing. But the limit from the left was the same as the limit from the right, therefore the limit exists. So the limit as x goes to 3 of g of x appears to exist. And then we can say what that value is. The value is the common number there. The limit as x goes to 3 of g of x equals 5. So let's take a look at one more sort of question here. This time I'm going to go with a piecewise function, one of our favorite sorts of functions to use in calculus. We are going to say the following. F of x equals 2x plus 1 if x is less than or equal to 3, and it equals 5 minus x if x is greater than 3. So we need to look at what happens as we approach 3 from the left and what happens as we approach 3 from the right. So x, f of x. So approaching it from the left to 3. What happens at 3 is irrelevant. What happens near 3 is what we're interested in. So how about 2.9, 2.99, 2.999. And you see for all of those, we're on the first branch of our piecewise function. We're on the 2x plus 1 part. So let's do 2 times 2.9 plus 1, etc. So 2x plus 1, 2 times 2.9 plus 1 gives me 6.8. Let's look at 2.99. So 2 times 2.99 plus 1 gives me 6.98. They seem to be heading in a certain direction. And then 2 times 2.999 gives us 6.998. So what do we have here? All of these numbers, x is getting closer to 3 from the left. So we'll take the limit as x approaches 3 from the left of the values of the function. What are the values of the function seem to be getting closer and closer to? Seem to be getting closer and closer to 7. But now let's go ahead and try values to the right of 3. So we're going to close in on 3 from the right. So we'll go to 3.1, 3.01, 3.001. Well, notice if I'm bigger than 3, I'm now on the second branch of this piecewise function. So if x is bigger than 3, 5 minus 3.1 5 minus 3.1 gives me 1.9, very different. 5 minus 3.01 gives me 1.99, and 5 minus 3.001 gives me 1.999. So looking at those values on my table, as I approach 3 from the right, these seem to be approaching 2. So the limit as x approaches 2 from the right of f of x seems to be, excuse me, approaches 3 from the right. 3.1, 3.01, 3.001, getting closer and closer to 3 from the right is 2. So the limit as x approaches 3 from the left of f of x is not the same as the limit as x approaches 3 from the right of f of x. What is my conclusion then when that happens? Conclusion, the limit as x approaches 3 of f of x does not exist.